Good morning and welcome to this Axiometric Solutions webinar. Today's subject is measurement microphone calibration. My name and your presenter for today is Ole Teilgaard. I'm Director for Global Support and Applications for two of the totally three brands in the Axiometric Solutions group. So I'm taking care of support and applications for audio precision, AP, and for grass, sound and vibration. Today's agenda is, first of all, we will have a little introduction to calibration. We will have a look at what is an acoustical calibration. We will look at quality in measurements. We will look of how often must I actually calibrate and why should we actually calibrate. And then we will also have a look at the calibration pyramid. After that, we will have a look at the IEC 61094 standard. It's actually the standard for measurement microphone. And we will have a closer look at some of the chapters telling us about calibration. We will talk a little bit about primary calibration, and then we will actually use most of our time on secondary calibration. We will look at secondary calibration, sensitivity calibration. We will look at secondary calibration for frequency. We will also have a short look at secondary calibration for free field calibration in the free field. And then we will also have a talk about low frequency calibration. By the end of this presentation, then I will give a demo, about 10 minutes, of the grass sound or vibrations microphone calibration system. And after that, there will be time for, hopefully there will be time for some questions. And please use for questions, use the Q&A function in this webinar, which you actually can find in the upper right corner of your screen. Introduction to calibration. For making documented, traceable, and approved measurements, your measurement equipment need to be calibrated. Calibration is a method that establishes a relationship between a measurement device and its measurements of units. Let's take a little example. If we have a ruler and we would like to calibrate this ruler, then we know that a meter is actually defined as the length of the part traveling by light in vacuum in about 33 nanoseconds. And when we have this relationships between the ruler and the standard for 1 meter is established, then the ruler can be calibrated, and we can have trusted data for the ruler. This is, as we saw before in the little example, done by comparison the device or the output of an instrument with a standard with a known characteristic. What is acoustical calibration? Yeah, it is actually calibration. Calibration means comparison of a value indicated by a measurement instrument with a nominal value that is provided by a given standard. When we are talking about acoustical calibration, then we are actually talking about pressure, and we are normally, when we're talking about sound and acoustic, measuring this pressure in Pascal. So we are referring to Pascal, pressure in Pascal. The equipment used for the calibration must itself be suitable, calibrated to ensure an unbroken trace back to the standard kept as at a national or an international institute. So we need actually to have a traceability for our calibration back to next level of standard. Quality measurement. For performing a quality measurement, you must keep these factors in mind. Let's see on these factors. First of all, resolutions. Does the measurement meet the requirement of the application? Accuracy. Does the measurement reflect to the true characteristic of what is measured? 3. Precision. Do you get the same result each time you measure the same quantity? The accuracy of the calibration needed is directly dependent on these considerations. How often should we calibrate? This is actually a question we receive quite often. And it is also a question that's very, very difficult to answer, because it depends on type of measurements, as well as the type of your quality assurance system. But I will try to give you some guidelines. When you receive a new instrument, then it's actually a good idea to perform a calibration, so you know how this new instrument is performing. When a specified time period has elapsed, often 1 year, then it's a good idea to do a calibration. When a specific period of uses, operation hours, has elapsed, then it might also be a good idea to do a calibration. When an instrument has been exposed for extremely environmental changes, temperature, humidity, or static pressure, that might have affected its performance, then it could also be a good idea to do a calibration. For instance, if you use a microphone at a very, very high temperature, actually outside the microphone's temperature range, then it might be a good idea to check the microphone again. Maybe something had happened with the microphone. When an instrument has been subjected to shock or vibration that might have affected its performance, then it could also be a good idea to do a calibration. And of course, whenever you feel that the measurement results appear to be questionable, then it could be a good idea to check and verify and calibrate the instruments again to ensure that everything is okay. Why should we calibrate? Yeah, we would like to calibrate because we would like to fulfill some external requirements. It could be legal requirements, and it could be requirements coming directly from the standards. It could be for fulfilling internally policies. It could be our company quality assurance policy that we have to calibrate once a year or so on. It could be internally described policies telling us how often and how we have to do the calibration. And of course, when you have to answer yourself the questions, do I measure correct? Calibration will give you confidence in your measurements. The calibration pyramid. Many of you might be users of microphones and instrumentations, and it means that your instruments are normally at the level called working instruments. If you are a calibration institute or a calibration laboratory, then you might perform a traceable calibration or accredited calibration. In this case, then your reference, your instrumentations, they have to be traceable at least to a secondary calibration laboratory. The secondary calibration laboratory has to be traceable to a primary laboratory at national or international standard. In this webinar, we will mainly cover from secondary calibration and down. I promise you that we would have a look at the standard for measurement microphone, the IEC 61094. This standard consists of 8 parts, and when looking at measurement microphone, then part 1 and part 4 is actually the most important when we are looking, because these parts describes the specifications. Part 1 describes the specifications for a laboratory reference microphone, while the IEC 6109-4, part 4, describes the specification for a working standard microphone. Part 2 and part 3, they describe this how to and a method of how to do a pressure calibration, a sensitivity calibration, and a free flow calibration of a laboratory microphone, the primary methods. While part 5, 6, and 7, and 8, they describe how to do calibrations of working standard microphones. So for this webinar, we are looking mostly at part 5, part 6, and part 8. But I think it's a good idea just for understanding, also to have a look at some of the other parts in the standard. So we will actually start with the part 1 and 4. This actually describes the specifications for a measurement microphone. Part 1 describes the specification for a laboratory microphone. A laboratory microphone is also defined with 2 letters. LS means laboratory standard. 2, the number 2 describe that it's a half-inch microphone, and P type describe the type of the microphone, P for pressure. This is actually equal to the GRASP laboratory reference microphone 40 AU-1. In part 1 of the microphone measurement standard, there are a lot of different parameters you have to fulfill to be able to call your microphone for a laboratory reference microphone. These are sensitivity, frequency response, dynamic range, the size of the microphone, environmental parameters such as static pressure, temperature, and humidity, stability, both long-term stability as well as short-term stability. There's a huge set of different specifications you have to fulfill. We actually see the same for the working standard microphones. WS for working standard, one for the size of the microphone, the number one is for 1 inch, P for pressure, 2 for half inch, P for pressure, free field and diffuse field, and WS 3 is for a 1/4 inch microphone, and again P for pressure, F for free field, and D for diffuse field. It's the working standard microphones, and it's actually all 1 inch, half inch, and 1/4 inch measurement microphones covered by these standard. Some of you will also say, hey, we do also have 1/8 of an inch microphones. Yes, but the 1/8 of an inch is actually not described in the standard, but most of the manufacturers of measurement microphones who is actually making 1/8 of an inch microphones, they are actually producing 1/8 of an inch microphone according to the standard. So you will also, for a 1/8 of an inch microphone, have the same set of data as well as the same size, the right size and things like that. If we look for laboratory reference microphone, then we are actually looking for primary calibration, and we will have a short look at primary calibration. In chapter 1, or part 1 of the measurement microphone standard, we have a method of how to do a pressure calibration, reciprocity calibration of a microphone. The principle in this is that we have a little coupler or chamber, and in this chamber we have our reference microphone, and we have our microphone under test or under calibration. The DUT microphone is called here on this slide. And the principle for free field calibration, we are doing something similar. We have a little chamber, a free flow chamber, where we have a microphone, a reference microphone, and a microphone under calibration, and these microphones are placed close to each other, as we saw before with the pressure calibration method. The way this is done when we are doing the reciprocity calibration is that the reference microphone is first used as a transmitter and then as a receiver, and the same for the microphone under test. We will first use it as a receiver, so it will actually pick up the signal generated by the reference microphone, and then after that we will use the microphone under test as a little speaker, and then we will use the reference microphone for measuring. And yeah, mainly used in this technique is mainly used in primary calibration laboratories. And then we actually have part 7, values for difference between the free field and the pressure sensitivity levels of laboratory reference microphones. It actually describes how to calculate what we actually call the free field corrections of the laboratory reference microphones. If we look at working standard microphones and we look at how to do sensitivity calibrations of working standard microphones, actually, then we will actually use the IEC 61094 4, that's 5 part of the standard. The principle of is that we are with the comparison method is that we are comparing our microphone on the test with a reference microphone. When they are either simultaneously or sequentially exposed for the same sound pressure level. If we look at the little drawing we have here, then we can see we have a coupler, and inside that coupler we have a sound source, a little speaker in this case, the reference microphone and the microphone on the test. These two are placed very close to each other, so we believe that they will actually see exactly the same sound pressure level. And if we know the reference microphone, the sensitivity for the reference microphone, then it's easy to calculate the sensitivity for the microphone on the test. Comparison can be done either with a reference microphone, as we have here on this picture, or it can be done with a calibrator, with a piston phone, or a sound level calibrator. Of course, the sound level calibrator and also the reference microphone, it has to be calibrated at a reference laboratory. If we have a closer look on a coupler where we are using a microphone as a sound source, then the diagram looks like this. We have our reference microphone again, we have our microphone on the test, and then we have a microphone as a sound source. It means this microphone will just work as a little speaker. With these techniques, we will actually be able to obtain a frequency response from approximately 20 Hertz to about 20 kilohertz. We will be able to generate a test level of around 100 dB. If we look at the one we saw before, where we actually are using a speaker as the sound source, then it looks like this. We have the speaker, we have the reference microphone, we have the DUT. Here we are able to get frequencies from about 250 Hertz and up to 16 kilohertz. 250 Hertz is due to normally the speaker here is a rather small speaker. Level from about 70 dB up to 110 dB in this neighborhood. And then we actually have the third principle where we are using a piston phone. A piston phone is a very precise sound source based on volume displacement. With the piston phone, we have a fixed frequency. It's normally 250 Hertz. We can have the level is also fixed, but we can have different types of piston phones. We could have 94 dB inside the coupler, 114 dB, or even higher, maybe 134 dB. 114 dB is quite normal to see. We will have a closer look at the principle in the piston phone. So let's go to next slide. On next slide here, we have actually the piston phone. As I mentioned before, the piston phone is a very precise sound source. It is based on volume displacement. And it means that we have the pistons. It's actually here, we have the two pistons. And these two pistons, they will move when this cam disc is turning around. This cam disc is controlled by an electrical motor. So this cam disc will turn around, and when the disc hit the pistons, then the pistons will move, and it will actually build up a pressure inside the coupler. So it is actually a very precise pressure. But this pressure, as we have no feedback from we are not compensating from the atmospheric pressure directly in the piston phone, so we actually have to manually to compensate for the atmospheric pressure. The frequency of the piston phone is 250 hertz. If we would like to be very precise, then it's 250.2 hertz, and 251.2 hertz is actually the exact center frequency of a 1/3 octave 250 hertz filter. It is very precise. It is a very precise measurement equipment. 114 dB equal to 10 Pascal. We also have to have a little look at a sound level calibrator. Let's have a look at the Grass 42AG. The principle in the 42AG is that we have a little speaker, a little loudspeaker, and this loudspeaker will actually generate a tone, 250 hertz or 1 kilohertz inside the coupler, which will be picked up by the microphone. To regulate that, we have a little pressure sensor, and this pressure sensor will actually make a feedback loop. So we have an automatically gain control. So we will generate exactly the level which we would like to have. It could either be 114 dB or 94 dB inside the coupler. The level calibrator will also measure the atmospheric pressure, so we will actually directly compensate for the atmospheric pressure inside the sound level calibrator. So it's not necessary after to do a compensation for the atmospheric pressure when using a sound level calibrator. The 42AG from Grass is a high precision, multifunction, and easy to use sound level calibrator. It conforms with the standard for piston phones and sound level calibrator, the IEC 60942. It has two frequencies, so we actually have the possibility for doing a frequency linearity of our measurement chain, as we have 250 hertz and 1 kilohertz. We can also use it for testing equipment where we have an A-weighted network in our measurement chain, because by use of the 1 kilohertz, at 1 kilohertz, the A-weighted network gives us 0 dB. We have two levels, 94 dB and 114 dB, so we actually have the possibility for making a level linearity check of our measurement chain. And as a bonus, we will also have the environmental data for our documentation of our measurements. It's data like air pressure, temperature, and humidity. Let's have a look where we are comparing the sound level calibrator with the piston phones. Let's start with the sound level calibrator. The sound level calibrator is for verifying of your measurement chain. The sound level calibrator is for free field use, for daily use, to be used with all standard measurement microphones. We can also use it with low noise microphones due to we have this 94 dB mode. We don't need to do any corrections for the static pressure. We don't need to do any corrections from the front volume of the microphone. We need to do a correction for a half-inch free field microphone with 0.0 0.15 dB, and it's actually due to a free-float microphone. We are of course measuring the pressure inside a calibrator, and a free-float microphone will, if we look at the pressure response, fall off with 0.5 dB at 1 kilohertz. So the correction is only for half-inch microphones at 1 kilohertz. Let's have a look at the piston phones. Piston phones are for calibrations of microphones and microphone sets. Piston phones are for laboratory use. They have a very high precision, 0.08 dB, and with an accredited calibration, you can actually get a very, very high precision, 0.05 dB. We have to correct for the static pressure, and we also have to correct for the front, for the microphone front volume. So the sound level calibrator is actually for daily use. It's for it to be used in the field, so it is not to be used for secondary calibration laboratories. It is a working instrument you are using in the field. The piston phones, they are actually the laboratory instruments, and they are perfect to use for secondary calibration laboratories. Let's have a look at the microphone sensitivity. When we are making a measurement of the microphone sensitivity, then we are talking about an open circuit sensitivity. The open circuit sensitivity is the sensitivity of the microphone when it's not loaded by the preamplifier input. So we have no preamplifier gain. We are actually only looking at the capacity of the microphone itself. We also have another parameter called closed circuit sensitivity. The closed circuit sensitivity is actually the output of the microphone when it is mounted on a preamplifier. And all of us know that we can actually not use the microphone without mounting it on a preamplifier. So what about this open circuit sensitivity? It is actually only the sensitivity of the microphone capsule itself. It's not the sensitivity we will measure on the output of the preamplifier. If we look at the little electrical diagram we have here, then we have our microphone, and we have a capacitor in our microphone, the CM. If we look in the preamplifier, then the preamplifier consists of an input impedance, a big, large input impedance, and it will also consist of a little capacitor, the capacitor in this diagram called CS. So we will actually have a voltage division between our microphone capacitor and the capacitor in our preamplifier. And this will actually give a damping of the microphone signal. And as preamplifiers are different, and maybe we would like to use the microphone on many different preamplifiers, therefore we need to know the open circuit sensitivity for the microphone capsule itself. We can calculate this, the closed circuit sensitivity, by the formula given here. If we have a closer look again, open circuit sensitivity is for the microphone, is only for the microphone capsule. It's independent of the preamplifier mounted on the microphone. It's a standardized value, it's a standard calibration value. It's it is actually not very practical to use, because when we have this value and when we mount the microphone on the preamplifier, then we actually have to do some compensation for finding the right calibration value for our combination of the microphone capsule and the preamplifier. But this value, the open circuit sensitivity, is actually an IEC standardized value. Closed circuit sensitivity is when the microphone is mounted on a preamplifier, and it's actually the sensitivity we can measure on the output of the preamplifier. So it depends, of course, of the preamplifier, and it is actually not an IEC value. It's not a parameter in the IEC standard, but it is a very practical value, because we can use this value directly to enter to our analyzer or data acquisition we are using together with the microphone. So the analyzer and data acquisition actually knows and can be adjusted for the right sensitivity of the microphone. Let's have a look on how we actually are doing these open circuit sensitivity calibration. First of all, we are actually using a special preamplifier for doing these calibration. We are using an insert voltage preamplifier. The insert voltage preamplifier, the benefit of that one is that we have a possibility for applying an input voltage via the amplifier and actually directly to the microphone itself. And in this way, we are actually able to do an open circuit sensitivity measurement of our microphone. The procedure for doing this is, first of all, we will apply a very, very well-known signal to a precise signal to our microphone, and it's actually done via the piston phone. So we will switch on, we will mount the microphone inside the piston phone, we will switch on the piston phone, then the piston phone will build up a very well-defined sound pressure level, let's say 114 dB. It will be picked up by the microphone, and then we will actually just measure the output voltage on the output of the preamplifier. We will store this voltage, keep it, and then we will actually switch off our piston phone and we will switch on the generator. When we switch on the generator, then we will, as we can see here on the drawing, then we will actually use our microphone as an input capacitor. So we will actually put the signal via the microphone to the preamplifier. And then we will measure the output voltage of the preamplifier. It's the voltage we call V2. The generator voltage, we actually have something called V1, and we will actually adjust V1 until V2 is equal to what we actually saw in step 1, where we were measuring with the piston phone and just measuring the output of the preamplifier with the piston phone on. When we have adjusted V1, the generator level, so it's equal, so V2 is equal to VO, then we can actually measure V1, and V1 is actually equal to the open circuit sensitivity of the microphone, actually the unloaded sensitivity of the microphone, because now we know how much we actually have to apply to the microphone to get the same output as we saw before. Here is a typical setup for doing exactly this type of calibration. We can use one of our analyzers from AP. This analyzer will be connected via a power module, the 12AK-S3. This power module supports actually insert voltage. We have an insert voltage amplifier on which we have mounted our microphone on the test. We have the reference piston phone. So we switch on the reference piston phone. We have switched off the generator signal, and then we just measure the output of our preamplifier and our microphone. We keep this output in our analyzer, and then we switch on the insert voltage, and we adjust the insert voltage until the output is equal, and then we measure what we actually apply to our insert voltage, and now the insert voltage is equal to our open circuit sensitivity. The piston phone level must be corrected for the atmospheric pressure, as we talked about before. So we can actually use this formula for doing this compensation or corrections. And then we also have to correct it for the microphone front volume. So it ends up with that the corrected piston phone level is actually equal to the nominal level for the piston phone plus our static pressure corrections plus our volume corrections. When we have done this, then we know exactly the sound pressure level for the piston phone, and now via this level we can actually calculate the sensitivity of the microphone. The microphone sensitivity, according to the standard, then we actually have to measure the microphone sensitivity in millivolt per Pascal or in dB relative to 1 volt per Pascal. And yeah, we measure the level, and then we can actually do the comparison and do some measurements. And it's actually showed here. And when we have our measured level, then we can actually calculate the sensitivity in dB relative to 1 volt per Pascal. When we are talking about calibration, then we also have to talk about uncertainty and the budget for uncertainty. The budget for 1 inch and half-inch uncertainty is, first of all, we had to have a look at the uncertainty chain. We have an uncertainty in our reference microphone. We might have some distortion, which also will give us some uncertainty. We will have some uncertainty due to stability in our reference piston phone. There will be some uncertainty due to we have different temperatures. There could be a temperature deviation. We could have there will be uncertainty as we have to correct for the static pressure. There are maybe also deviation in the humidity, and there are also some uncertainties on our voltmeter we are using for doing these calibrations. All these uncertainties, they will actually be added together. It means uncertainty 1 might be weighted, so there will be a weighting factor, and then we take the square of that, and then we add all the uncertainties we might have in our whole measurement chain. And in the end, then we actually have to make the expanded uncertainty K equal to 2 by using of the formula here. and then we have actually calculated the totally uncertainty for our sensitivity calibration. So this is actually the uncertainty budget for a 1" and ½ microphone calibration. And we can actually see that the expanded uncertainty is equal to 0.073 dB. Frequency calibration of the frequency response. For doing this, according to the IEC 61094-6, we need a generator, an analyzer, we need an electrostatic amplifier able to generate a high DC voltage as well as a high AC voltage, and then we need also the electrostatic actuator. The principle in the electrostatic actuator method is that we have a generator able to generate, it could be from 100 Hertz up to 200 kilohertz, or maybe 20 Hertz. I will come back to that, up to 200 kilohertz. Then we have an AC amplifier because we need a high AC signal. We can actually see up here, we need an AC signal of approximately 100 volt RMS. And then we have our very high DC supply, 800 volt. And the 800 volt together with the 100 volt AC signal, it will be applied to our electrostatic actuator. The electrostatic actuator will be mounted on the top of the microphone, and then we have a preamplifier, and then back to an analyzer, so we are able to do the measurement. Let's have a closer look on how this electrostatic principle is working. The electrical plates in our actuator will actually be very, very close to the diaphragm of the microphone, and it will be 100% parallel with the diaphragm of the microphone. So these two plates will actually form an electrical capacitor. The actuator plate and the microphone diaphragm. Between the capacitor plates will the actuator produce a force which will actually be distributed over the entire diaphragm of the microphone. And as long as the applied AC and DC voltage are kept constant, kept at a constant level, then the force is actually frequency independent. That's a formula we can calculate. And but if we look at the levels, the expected levels, if we have 800 volt DC and AC of 100 volt, then we are able to get a sound pressure level of approximately 2 Pascal, and so on for different AC levels. The actuator methods can be used in a very large frequency range, actually from about 20 Hertz up to 200 kilohertz. The standard describes actually from about 100 Hertz and up. And I will come back to what's happening at low frequencies, but at the higher frequencies, there might also be some small uncertainties. And it's actually due to there will be a little deviation in pressure because the diaphragm is moving, and when you have the moving diaphragm, then it might work as a resistor at higher frequencies, and when it works as a resistor, then the sensitivity will fall a little. as we actually can see here, it's not absolutely linear or at the same level over the entire frequency range. So therefore, we have to do some small compensation when we are using the actuator. Small compensation in the pressure response, higher compensation when we are talking about free flow microphones and random incidence microphones, because they have to be compensated so they are measuring correct when they are used in a free field or in a random incidence field. So the actuator response we are obtaining, it has actually to be corrected for the pressure corrections, it has to be corrected for free field corrections, or it has to be corrected for random incidence corrections. The pressure corrections is normally so small as it's not necessary to do any corrections. It depends on type of microphone. Low frequency cutoff, the electrostatic actuator method can be used down to approximately 5 to 10 times the lower limit, frequency limit specified for the microphone. The IEC standard says 10 times, and it's actually due to you will have some limitations at lower frequencies because the venting system of the microphone capsules will actually at low frequency, or can at low frequency be seen as a reduction of the total stiffness of the microphone capsules, and therefore will the microphone capsules be more sensitive at lower frequencies if an actuator is used. Let's have a look. I have actually measured a low frequency response of a microphone. The green curve is actually the actual low frequency response for the microphone. The blue curve is measured on with an actuator, and we can actually see that it starts falling off later than the actual the right low frequency cutoff. Actually, theoretically, the low frequency cutoff when used with an actuator should be like the dotted line here, but it's not like that. It is actually like the blue line, and it's actually due to the electrical cutoff in our electrostatic amplifier and in our microphone preamplifier. Also, for actuator response, we need to have an uncertainty budget for the microphone, and it's more or less the same chain as we saw before. There's a lot of different parameters in the chain. The way of doing the calculations is the same as we saw before under sensitivity. So here's the table for all the different parameters we have to take into account. And in the end, we end up with an expanded uncertainty equal to 0.17 dB. Part 8 is actually this free flow calibration of working standard microphones with the comparison method. There are two methods we can use: a basic subtraction calibration in a free flow chamber, in an anechoic chamber, or we can use the time selective techniques. Basic subtraction calibration, we need a sound source. It could be a speaker or a microphone. We need a reference microphone with a very well-known frequency free flow response. Of course, we need the microphone on the test, and the procedure is, first of all, we measure the free flow response of the reference microphone. Then we mount the microphone on the test in exactly the same precision as the reference microphone was mounted in. And then we measured the response of the microphone under calibration. And of course, when we're doing this, then we are assuming that the acoustical centers of the two microphones is exactly the same, right? And is in exactly the same point. We also assume that the sound field remains the same. So no changes, because otherwise we can't use it. And then the free flow sensitivity response is found by the ratio between the reference microphone and the microphone under test. Time selective techniques, we need the same components as we saw before. The principle in the time selective principle is that we don't want to have the reflections from the wall, from the room, interrupting, disturbing our measurement, our calibrations. So therefore, we only want to look at the direct sound, the sound equal to what we actually have here from number 3. The way to do it is actually using an impulse response. So we will generate an impulse from the speaker here. And then we will look at the energy time curve. And then with the green cover here, we will only look at a part of the curve. We will not look at the reflections from the room. So we will only look at the at a few seconds of the signal. And by doing this, then we will actually be able to look at a nice frequency response. And by using of the same calculations as we saw before, then we can actually find the free flow response of our microphone under test. So we need actually an analyzer with software for calibration of free flow in a free flow chamber. We need to be able to measure a frequency response. If we use the time selective techniques, then we need acoustical response and be able to measure with this time selective functions. Low frequency calibration. For calibration below 5 to 10 times of the lower frequency of the microphone or microphone set, we can't use the actuator. A piston phone principle can be used, and that's actually what we actually have here, where we actually are using a speaker at this low frequency. Then the cone of the speaker will actually more or less work as a piston moving up and down, and that way actually generating a pressure inside the coupler. This pressure is actually, or the force is actually equal to the magnetic field we have in the speaker times the length of the coil, the speaker coil, times the current we have. So we are actually able to measure the force by having a little current sensor. Then we can easily calculate and measure the force, and in that way also be able to measure the pressure inside the coupler. For having a higher accuracy, then we could eventually have a reference pressure sensor, so we know exactly what the pressure is inside the coupler. Of course, when we are doing this type of measurement, then the venting system of our microphone on the test, it must vent into the test chamber. It must vent into the coupler. For calibrations of microphone capsule, is it recommended to use a preamplifier with an extra high input impedance, actually to avoid conflict between the acoustical and the electrical cut-off of the microphone capsule. It's not an issue when we are talking about microphone sets where we have combined the microphone and the preamplifier together, because here we are only interested in to know what is the low frequency response of the combined unit. Calibration equipment we have been talking a little bit about today is the Grass multifunction sound level calibrator, which can be used for sensitivity calibration. Our piston phones 42AA, AP, and AC, also for sensitivity calibrations. The 51AB is a phase calibrator. It's actually a two-port calibrator, which can be used with the comparison techniques, both for sensitivity and frequency. The Grass 42AE low frequency calibrator for making the low frequency response of the microphones. The 14AA electrostatic amplifier for generating the high voltage, and the electrostatic actuator itself. And in the end, the Grass microphone calibration systems for calibrating of microphone measurement sets and preamplifiers. This system is both covering sensitivity and frequency response. I know that I have spent 1 hour. I have a demo now, 10 minutes. So if you would like to see the demo, then you just stay. And if not, then thank you for participating. I will start this little demo. It's working now. Yes. When you start up the system, then you have to, of course, to tell who's the operator. You have to enter the test conditions, barometric pressure, temperature, and humidity. The barometric pressure is actually normally automatically read by the built-in barometric pressure sensor in our piston phone. When we have put in the test conditions, then we say, hey, now we would like to do a new calibration. So we press new calibration, and then we select the microphone we would like to calibrate. We can calibrate microphone capsules, and we can select the microphones from the list we have down here. We can also calibrate microphone sets, where we also have the possibility for selecting these sets from the list. We can also calibrate not microphone sets, but a combination, random combinations of microphones and preamplifiers. So we can select which of them we actually would like to calibrate. But what I have here is a Grass 40AG. It's one of my demo microphones. So I will select the 40AG. I will put in the serial number for my 40AG. I have actually a possibility for telling a little bit about the customer ID, calibration ID, and customer items ID. Things like that can be added. I can also select which frequency I would like to start from. I would like to start from 20 Hertz, so I did that. So we can see test conditions is in the system. We also have what type of microphone we would like to calibrate, serial number, and things like that. Then we can actually see that we have two level buttons. We have one called level calibration and the other one called level calibration 2. Level calibration is our reference calibration where we are using our reference microphone. With level calibration 2, we can use another calibrator. It could be another piston phone. It could be a sound calibrator, so we can calibrate at another level or at another frequency. I press level calibration, and the system is starting up, and we can see that slowly the sensitivity is actually building up on the microphone. This is an externally polarized microphone, so there are a certain time constant for the the polarization voltage to be built up. There's a time constant between the microphone capsule and the input impedance or the resistor in our amplifier for our polarization voltage. Now it actually have built up, and before I knocked in the table, and you can actually see this high signal coming up. What we actually see here, we have a white graph. The white curve is an instantaneously curve, and the red curve is an average curve. When the little green lamp lights up, then we are actually ready and everything is stable. This is a calibration of a microphone capsule, and only the microphone capsule. So we actually had to find the open circuit sensitivity. So therefore it made it in two steps. First with the piston phone on, and secondly with the piston phone off for making the insert voltage. And we can now see here that we actually have measured everything. We have the sensitivity in millivolt per Pascal. We do also have the sensitivity in dB relative to 1 volt. We have a deviation of 1.27 dB, and it's actually a deviation for the nominal sensitivity of that type of microphone. But we have the green light lamp, and everything is actually within the specifications. I will now press the frequency calibration. And we can see here that the frequencies is stepping up, and now it is actually finished. But we can also see that it looks like that we have some issues in the low frequency range, and it's actually also building up. And it's again this polarization voltage that have to be stable. Now we can see that it's stable. We have actually a nice curve, but still we do have a little issue at the lower frequencies. And it's actually due to, I have forgotten that we have a high pass 20 Hertz high pass filter in our system. So I will switch off this 20 Hertz high pass filter. I can also see that we have a little issue at 20 kilohertz, but we will do it again. And now we can see that everything is actually okay at the lower frequencies, and it was actually due to this high pass filter. But we still have a little issue at the high end. We will run it once more, and this issue is actually due to it's my demo microphone, and I know that it's a 0.01 dB off at 20 kilohertz. It's hitting the tolerance. I will accept this curve because now I have actually done the sensitivity calibration, and I have also done the frequency calibration. The sensitivity calibration was okay. The frequency calibration has a little issue at 20K. I will say, okay, I will save the data. And when I have saved the data, it's actually what I call the raw data. So we have the frequency response, the whole curve and things like that in a table. And I will also generate a PDF file, a calibration certificate, a nice calibration certificate. And now we actually have green lights. If we would like, then we have to have the possibility for looking at the results. If we had done more than one calibration or an old calibration, a year or 10 years old, then we could actually compare the result we just have made with the old one and see if the microphone has moved, if something had happened with the microphone. And it can be looked at in both sensitivity level and also with the frequency response. As I mentioned, yes, then it's a little bit off at 20K. If we look at the definition, the microphone definition, then there's first of all, we can actually see how the level piston phones are performing. We can see the serial number, we can see where it is communicating with the computer, the COM port, we can see the frequency, we can see the nominal level, actual level, and we can also see the uncertainty. And if we are using different types of couplers, then we will also have other values for these couplers. We also see all the data for the microphone here, type of microphone, half-inch microphone, it's a pressure microphone, it's a polarization voltage is also indicated. We also have the possibility to see where we are storing the calibration results, both the raw data and the calibration certificate. We can also see the different templates we are using for generating the calibration certificate. And we also have all the data for our frequency response. Then we have a list of all the equipment we have used for doing this calibration. This was actually the words of and the demo of our calibration system.